going over these points. Alright, so starting with section 6.1. So you have to know, first of all, what I mean by joint probability mass function or joint probability density function. So that's just, if it's probability mass function, physically what it means the probability that x equals x and y. And it has to be a number that's greater than or equal to 0. It's also some numbers that when you add up over all x and y values, they have to add up to 1. The continuous analog of that is you have a non-negative density function, and it integrates out to 1 again. The way you understand it is if you're interested in finding the probability that x and y lie in some region, it's just the integral of your density function of that region. So this is something some people still have a problem with. Whenever you're asked a question that about some event, the probability of some event, and that event involves both x and y, you're asking about the probability that x and y lie in some region. So the probability of event involving x and y. So probability x greater than y, or probability x greater than 1 and y less than 2, something like that. So these are examples of probabilities of something involving both capital X and y. Is basically you integrate over the region where this event is satisfied. You integrate the density function over that region. X and y satisfy this condition. So maybe I shouldn't say event. I'll just stick with region. So, for example, if it's the probability that x is greater than y plus 4, there's some event involving both x and y, you're basically going to integrate over the region, set of all xy, where x is greater than y plus 4. So if you have a joint density, you can answer questions of probabilities of events involving both x and y. Alright, so that's what we mean by joint probability mass function. And then that brings us to marginal. That's a marginal probability mass function. So in terms of discrete, is if you're given the joint probability mass function and asked to find the marginal, it says if I want the marginal probability mass function for x, I sum out to the y's. Okay? If I want probability, the marginal density function for x, I integrate out the y for my joint density.
What was the first line that you said? That's if you want.
I want the probability mass function only of x.
Mm-hmm.
And I have the joint probability mass function.
Mm-hmm.
So that means I only want the probability that x takes the value little x. So x can take the value little x, while y can take everything.
Mm-hmm.
So I just sum up all the probabilities that x takes little x and y can take whatever.
Second line. Is the first line discrete, second line continuous?
Yeah, that's the only difference here.
What did you call them again?
Probability mass function?
For both, right?
No, probably density function.
Oh,
Density.
that's right. Densities for the.
Okay, that's
Continuous.
chapter 1 of yours.
I was just talking vocab here, just a little mixed up.
In that sense, this class is cumulative, this final. You need to remember things like probability mass function, density function.
We've just been using it so much, I forgot which one was which. Oh,
okay, so density function, all right. So if I give you the joint probability mass function or density function, and I ask you to find the expected value of x, what should you do? You can just calculate the marginal probability mass function or density function for x, and then use that to calculate the expected value of x. So again, this is like chapter 1 or 2 material, but you're going to be tested on it even in chapter 6. So that's for discrete. Continuous. And here I want the expectation of x. And if I give you the joint probability mass function or density function, you first need to calculate what these are, the marginals, so that you can use that in your definition of expected value effects. All right, so that's joint probability mass function and the marginals. And then if you're talking about two random variables, I can talk about, ask the question of whether they're independent or not. Independence is the next important section that we work on. And we say that x and y are independent if and only if they were discrete. That means their joint probability mass function is just the product of their marginals in the discrete case, or means, and this is for all x, y. If they're continuous, the joint density function is just the product of their marginals. Again, this is for all x, y. So that's when you're talking about independent. So if they're independent, the joint probability mass function of the joint density function is just the product of the individual. So if you want to prove that something is not independent, all you need to show is that this is not satisfied for some x and y.
So you would solve for each independent, multiply them together so that it's not the same, right?
Exactly.
So
Yeah.
you have
For some values x and y.
So you would have to use the joint to solve for the two individuals, correct?
Right. You would first have to do this
To sum over
to get the marginals, right?
Okay.
And then you would check whether for some x and y values, specific x and y values, the joint is not equal to the product of the individuals.
And if they are equal, does that make, does it go
You
back?
have to then check for every x and y. And
For
then
all
get,
x
yeah.
and y? Okay.
So to disprove it, that is to show that they are not independent, you need to just check.
one.
Yeah. And if it turns out to be not true for one, then
You're
they're
done.
not independent. Then you're done. But if you want to prove independence, you will have to check it for all x and
For
y.
all x and y.
Yeah. So if you check it for one x and y and it's satisfied, you can't just say that, okay, they're independent. You need to check.
Keep trying.
Keep
Okay.
trying. So keep trying until you get them not equal. So then you can say they're not
Then they're
independent.
not, okay.
But there is a way of showing that they're independent without checking for every possible value, and that is by this theorem which says that if, so let me just say for the density function, but the same thing is true for probability mass function. If your density function, you notice that it can be separated as a function of x, let me say f. If I can write it as, group the terms in the expression for this density function as a function of x times a function of y, then x and y are independent.
Can you say that one more time?
So there was a theorem that said that if your joint density function is like a function of x times a function of y, then you can conclude that they are independent.
Okay.
And in fact, that the theorem actually said then this would actually be just some c, some constant times g of x, and your f of y would end up being,
Oh, yeah.
remember that theorem actually, yeah. So in fact, if you can express this as some function of x times a function of y, then your marginals would end up being c times function of that g of x, and your marginal for y would be one c times that function.
So this is a better way to prove
But that's-
independence, and that's a better way to prove dependence.
Yeah, but
Okay.
you may not always be able to write it as a product.
And which doesn't necessarily mean that they're not independent. It just means we might
You
not be
won't
able to
do it, right,
manipulate it that
right,
way. Okay.
Yeah,
Does that hold for the discrete case too?
yeah, correct, yeah. Same thing, discrete, if this can be written as x of x, g of x, h of y, same thing. So that's checking for independence. There are many ways you can do that. Sure. Not independent by showing that this is not true for some x and y values. If the expression for your density function or mass function is such that it's easy to see that they can be decomposed as a product of function of x times function of y, then by just this theorem, you know right away that they have to be independent.
Okay.
All right. The other case where you will always get dependence is if your density function, and I say density function but also mean probability mass function, if this is non-zero in some region other than rectangle. So some region where your x and y are related to each other. Okay. So say for example, that's one of the most common things, right?
So by looking at that, we can tell x and y are dependent. Would we just say?
Exactly. Yeah.
Okay.
So from this, it's obvious because you can always choose some. You know that if you took y to be less than x, then your joint density would be 0. But you can show quite easily that the marginal density for f of y, to take the value, say 1/4, is positive.
Right.
And the problem, so you could always take f. You can say 1/4, comma 1. Yeah, 1/2, comma 1/4. Oh, that is 0. Okay.
Okay,
Because
yeah.
this is the region where it's non-zero. But you can show quite easily that fx of 1/2 is positive, and fy of 1/4 is positive.
Okay.
So that's independence. If you're calculating the expectation of something, which is an independent, if x and y are independent, then if I have some expectation, if I ask you to take the expectation of k of x and of y,
That's f of 1/4.
fy 1/4, y 1/4, and fx of 1. So if I know x and y are independent, and I ask you to find the expectation of some function of x times a function of y, then by independence we get that it would just be expectation of that function of x times the expectation of that function of y. And it's because of this, as a consequence of this, covariance of xy equals 0 when x and y are independent. Because what was covariance? So I'm kind of skipping ahead here, but covariance was, you can write it like this. And if they're independent, then I know that the expected by this theorem, this can be written as the expectation of x times the expectation of y. And then you're subtracting the same thing. We distribution of sums. Sums. We have independent random variables. If x and y are independent, and I ask you for the density function of this of x plus y, we have a formula for this, and that formula is fx z minus y fy y d. That's the continuous case. For the discrete case, it would be function of y x z minus y. So if x and y are independent, the density function of this, you don't have to try and derive it. We have a formula for that. Now, if x and y were not independent, then you cannot use this formula. If x and y are not independent, then to find, what do you have to do? You first find the distribution function of x plus y and z. That is just the probability that x plus y is equal to z. Just C. Just A. And this is just going to be the integral over the region x plus y less than equal to A, the density function. So you first evaluate that, then step 2, you find the density function of x plus y by taking the derivative of your distribution function of x plus y. That's the general method. Now, if it wasn't just sums that you were interested in finding the distribution of, if you want, okay, so let me write this next topic as distribution of functions of x and y. So if I ask you to find what is the density function of some function of x and y. Same method. Step 1, you first find the distribution function of this function of x and y. So that is the probability that this is less than equal to A. So it's basically the integral of the joint density over the region where this is less than equal to A. And then step 2 is to find the density function by just taking the derivative of the distribution function. Oh, not x plus y, some function of x and y. So say, for example, I wanted to know the distribution function of x squared plus y squared. So that is an example of g of xy. That's the distribution of x squared plus y squared. You first find the distribution function of x squared plus y squared. So what's the probability that capital X squared plus y squared less than equal to A? So for example, g of xy would be x plus y squared. So if I give you the joint density function of x and y, you can use this method to find the density function of any function of x and y.
That's a question mark or?
Yeah, that's a question mark. So you want to find the density function of some function of x and y.
Did you have a problem like that on the review?
No, I don't think I had any problems on the function of random. We have sums of independent random variables, but we don't have any other function.
Okay.
Yeah. So, yeah. And I think even the problem that I gave, the x and y, yeah, no, I didn't. So, yeah, so there was no problem on this, on your practice exam.
You said there was no problem like that on the,
On the practice exam, I mean on the practice problems.
but we should know how to
Well,
do
it's
it.
one of the topics I covered after the midterm.
Okay.
That's what I'm saying. All right. Some important points that you definitely need